Hi everyone, this week we will cover electrochemical energy storage, supercapacitor. So we know that we have to use a lot of energy, not only to stabilize the renewable energy sources like wind, solar, hydro, ocean, oceanation, and so on. We also actually need it for our EV or portable electronic cars. So many times we think about battery. In fact, we also have another electrochemical energy storage system that commonly used. So there are two. You can imagine them as a battery as a marathon runner that can supply you the energy constantly for a longer period. So whereas supercapacitor like a spindle runner that can give you a power in a very quick one and discharge it very quick and very shorter period compared to the battery. So when we refer to the energy storage, we will look into the graph, a plot at your left side, which is called Ragon plot. So for the light blue color is supercapacitor. Some of the people you call it as capacitor, that depends on the power and energy density that deliver. The concept is the same, the mechanism. Whereas for the battery, they have the chemical storage, chemical reaction, and thus the period is much lower, shorter, their lifetime shorter compared to supercapacitor. Supercapacitor can charge, the efficiency is nearly 100% and discharge and charge again more than 100,000 cycles. Whereas for battery, it's about 3,000, much lower cycles for that. So if you look at the chart on your left side, the y-axis, the supercapacitor can deliver you your power density more than 1 kilowatt per kg, right? Whereas the supercapacitor can deliver more than about 20 kilowatt per kg, whereas battery only able to deliver about 1 kilowatt per kg. But the good thing is the battery can deliver very high energy density. So it's up to 250 watt hour per kg, whereas supercapacitor is less than half of the energy density that battery can deliver. So it depends on your application to choose which suitable energy storage system for you. Right. So this is the energy storage graph. So for the red color one is the capacitor. For the purple one is the battery. So as you can see that the capacitor or supercapacitor, they charge very fast and they have a little bit of self-discharge if you leave it there for not using it, and then it will discharge very quickly. And it will give you a higher voltage. Well, for battery, it have a plateau voltage charge. Yeah. So, and then the good thing is battery don't have self-discharge problem, and it will gradually, slowly to deliver the voltage into a longer time. Current, for the current, so normally when we charging the capacitor, we need a constant current to charge, and we will deliver in a high power output. Whereas for the battery, you need a longer time to charge the battery, and then, however, it only deliver you the low power output, right? So let's have a look on the component structure of the supercapacitor. Well, you might ask, just now we're talking about supercapacitor, and in this slide, you're talking about capacitor. The difference is the material that you use in the electrode. If you have higher surface area, you can deliver a more charge. Yeah, so we call that a supercapacitor. You can find different type of capacitor in the market. Well, it depends on your application, depends on your power and your which one suitable for your to choose on it. Okay. So the yeah. So let's go back to the component structure. So for the supercapacitor, it's actually rolling a long electrode separated by a separator. You can be a paper in the between, right? And then you keep rolling it. So, and then you become a cylinder shape. So you also can become a sandwich, like on your right side. So you put a separator, okay, and sandwich with two electrodes and some spring to make sure they are not easily move around and cover it so that there's no any other reaction with the, the, the air. This we call as a coin cell. So you can make this, find it in my lab to make this. So for the commercial one, normally they use it in a cylinder shape. So same concept. The difference is how long and you um, rolled it, and the surface area determine how much power, how much charge for it. Well, this is the actual supercapacitor. If you cut it to half, you can see there are a lot of there's a separator, the light blue color, and sandwich with the activated carbon. It's just the same. And how we know how to um, choose the capacitor is actually based on three things. One is the capacitance, one is the maximum voltage, and the tolerance. So for example, for this ceramic capacitor, the tolerance is J. J means about 5%. So 10(3), this is the capacitance, right? Means that 10 times 10 power of 3. So it's about 10 nanofarad. So for 2D, for the maximum voltage, some of them, because it's the size is too small, so they use some code. So 2D means 200 volt, the maximum it can sustain, right? So like I mentioned to you, they have the activated carbon, they have the separator, they also have the electrolyte inside there. Can you see I put some water drop here? So the electrolyte is the one that wet have to be wet to allow the ion transfer between uh, uh, between the separator. So there are few type of electrolyte. So aqueous, water in salt, ionic liquid, and the commercial one is organic electrolyte. So if you look at this chart on your left side, okay, ambient stability means is that safe, stable in ambient condition, room temperature, room condition. So for aqueous electrolyte and water in salt electrolyte, they are safe, no any explosion reaction occur. Well, for ionic liquid and organic electrolyte, they have to be in a glove box or a clean room to fabricate the supercapacitor to avoid any oxidation and further affect the performance of the supercapacitor. So if you look at the voltage, the ionic liquid deliver the highest potential window, also voltage window. The commercial, the organic electrolyte could deliver nearly 3. Aqueous electrolyte, you can use it as acid alkaline as your electrolyte, but however, it's only able to deliver 1 volt. This is quite low, so people want a highest one. So in my lab, we are using the water in salt electrolyte, which is still in the lab scale that we could deliver in room temperature and deliver voltage between 2 to 2.5 voltage. So this is my master student. So what she do is she try to make the tray electrode set up. So we try to test the new electrolyte, and can you see there's a sharp rise of the line? So that is called oxidation. So we don't want this happen. We try to avoid it. So the one that very horizontal line, this is what we are looking for to find the potential window. So the electrolyte that she tested, it's water in salt electrolyte, one of it could reach 2.3 volt. So without glove box, without special equipment, so the cost reduced more than 200%. So there is a potential for us to look into the water in salt electrolyte for the as a commercial one. The only things that we are looking into now is try to ensure the stability in a long period. So it's just like the food. If you put your bread on the table and it will just rotten within 3 days to a week. So you put a little bit of a stabilizer so it could stable for a longer time. So this is the energy storage mechanism between the battery and supercapacitor. So if you can see that they are quite similar. The difference is the content of the electrolyte and the material of the electrode, the one that determine the changes, because battery could have chemical reaction. So this is the general structure of the layout of a supercapacitor as energy storage. So you need to have a charging unit. So this charging unit should have to have a stable, constant current, so that it could, when we provide the main power, so then it will then store in the supercapacitor. So we also need a charging unit. This charging unit, normally we use DC-DC converter. This is to deliver the power output, right? To power output and deliver as a load. Okay, so there are different ways we can play around with these charging mode. So some of the it depends. You can become constant power discharging. So if you look at the voltage and time, it will like gradually reduce. So this commonly use it for your LED driver, your CPU to protect your CP, your down converter. This is quite common design too. So the other one is constant resistance charging. Not much application on it, but I found one of the sharing that they use it as an electric screwdriver. So they want to deliver in a very quick one. So the voltage can deliver and very quickly deliver and finish. And then you charge again. So another one is we want to have a constant straight a slope for the voltage and time. This is commonly used it for electrical characterization that I commonly use it to test the new supercapacitor, right? So there are few general procedure of design in to choose which supercapacitor, whether you want it into a parallel or series. So there are few things that you need to know is what load do I want to drive, how much power and voltage do I need. So you have to identify the mode of the operation for the discharge process, like I mentioned to you. You want to be like which one? Okay, constant power, constant resistance, or constant current. This one we can adjust it. How long do I want to drive the load? So this one you need to do some calculation whether we want to put it in a series or parallel. So this one is quite common. So I put it in a YouTube for you to like easy to understand with, and calculate size of capacitor unit. How fast should the capacitor unit be charged? So and choose the power source. Calculate the charge time. So this one we will cover next lecture. Okay. Okay. Another one is the one that we need to consider is the self-discharge profile of each of the supercapacitor. So actually, if you are a technical person, you are actually looking into the current, the self-discharging, how is current drop. But normally in the market, they are more prefer into looking into how the supercapacitor could maintain the voltage. That is actually depends on the pre-polling time and the temperature that you use in your during your supercapacitor operating. So, for example, if you look at this chart, seems like the blue one, at temperature 25, they could maintain the voltage quite well, still above 2.2. Some of whereas for the green one, it dropped very fast, like within how many hours it dropped to 2 watt. So that depends on what is your application, whether you want to choose the blue one or the green one. Yeah. So, however, you have to remember that supercapacitor cannot deliver long-time energy storage. So it's commonly now used in electric vehicles. So for example, or in China, Shenzhen, let's see if I have the picture here. So if you look at the electric vehicle here, the green one is an actual real world application now in Shenzhen in China. They use the supercapacitor. They make a lot of station. So from one station to another station, after they will charge again and move in a short period, they charge again. So you can't deliver the energy as long as so you can't deliver the energy like in a car, but you can have many different stations to charge and to recharge back your vehicle. This could be used in the town, city town area. Another one is with like Nissan. They have the hybrid car. So what they do is they put the supercapacitor when they want to accelerate. They on the like the Ferrari. So they on the supercapacitor. They push uh the speed up the sport car to limit to have a higher performance. So that depends on what is our application. So next week we will touch about more about calculation and more application in supercapacitor. I think that's all for today. Thank you very much.